Okay, good morning everyone. It's very nice to be with you today. My name is Yves Mabiala. I'm working as a data scientist at Thales back in France. And I'm going to talk today about sequence learning and more precisely how we can use recurrent neural network to perform sequence learning in Spark. So I'm going to start by presenting what, in a few words, 2 to 5 minutes, what we are doing at Thales, why sequence learning is important to us. Then I'll switch to the presentation of sequence learning. What do we mean by sequence learning? And why is it so difficult, especially in Spark, to perform sequence learning? Then I'll talk about how we can use deep learning, and more especially deep recurrent neural network to perform that. And I'll end the presentation by describing 2 use cases that we built, one in predictive maintenance, and the other one dealing with sentiment analysis, or text classification. So a few words about Thales and big data. So maybe there are a few of you who don't know Thales. So Thales is quite a big French company. So we basically build systems in multiple domains, such as defense, such as transportation. For example, we build ticketing system in transportation. Whenever you enter a transportation network, you swipe your transportation card. This is data we analyze in order to understand the transportation patterns. In security too, especially in cybersecurity, we deal with cyber attack detection, for example. We build network probes. In satellite too, we build satellites. And also the ground station which analyze all the images and the video coming from the satellite. So multiple domains. And all this information, all this system, they basically produce a lot of data. So if I take the example on satellites, for example, it's petabytes of data, petabytes of image. So we need big data tools to process and analyze this data. And of course, for each of those information, the sequentiality, the dynamic of observation makes a great importance. If I take the example of cybersecurity, what you want to do, for example, is to analyze all the events coming from a user or a computer, but not take them independently. There is a sequence in that, and you have to take that into account. So sequence learning takes a great place in order to understand the monitor phenomena that we are dealing with. So what do I mean by sequence learning? So it basically refers to a set of machine learning tasks where you have statistical models which either has to deal with sequences either at an input, at an output, or actually both. We'll see that later. I'm talking about sequence in a general sense. There is a special case of sequence, which is temporal series, where the time plays a great role. But I will go beyond that. For example, in genomics, you have sequences of genes, but there's no time in that. And the goal of sequence learning is to basically understand the dynamic of a sequence in order to classify, for example, in order to better predict or even to better modelize the sequence. Some of the typical application is not exhaustive, but this is some typical application. Text, either of words or letters. There are 2 levels of sequence in text. One of the most classical tasks that you can imagine is, for example, classifying text, such as sentiment analysis, for example, where you have text as an input and you want to decide whether it's positive or negative. Another common task that is very common those days is what we call image captioning. So for example, you have an image at an input and you want to describe in a textual fashion what is the content of this image. So you have an image and at the output you want to generate a text representing it. Video, so video is sequences of image. And speech, in speech to text, for example, you have sequence as an input, which is speech, and you have sequences at an output, which is the text. So how is it typically handled, especially in Spark, for example? How do we handle sequence? It's quite difficult, actually, and often people, they do not bother. For example, in textual analysis, one of the most popular approach to model the text is to use what we call bag of words. Using a simple encoding, one-hot encoding. So basically what you will do when you have a text, for example, the last one, is to put 1 when the word is present and 0 otherwise. So it's very simple. It models the content of the text but absolutely not the sequence, especially in some very specific tasks, such as sentiment classification, when the order of the words makes a great importance. So it's absolutely not sufficient. Or sometimes people use popular statistical approach. So you have two kinds, basically. You have Markovian models or hidden Markovian models. There's a problem that this is basically short-term dependency. So x at the time k only depend at x at the time k minus 1. So that's a problem. If you want to go beyond that, you can do that. But you have to know that the inference algorithm for this type of, such as hidden Markov model, is quadratic in the state size. So it's very difficult to model a very long time dependency using this type of approach. Or if you are dealing with time series, you can use popular models such as autoregressive model, but it's mainly for forecasting and it's linear. So in some case, it's not sufficient too. So we'll see how we can go beyond that. So what is the link between artificial neural network, deep learning, and sequence learning? So a few words to start about neural networks. So they are basically statistical models inspired from the brain. So they are composed of many layers. You can view each layer as a projection of its input onto a new feature space. So the more layer you stack, the more capacities your neural network will have. And in fact, if we have more than two hidden layers, that's where we talk about deep learning. So basically, artificial neural networks, they are composed of two things: transformation operation and activation. Very simple. One of the most simple transformation is the affine one, which is written there. So it's basically a scalar product between the input and the weights of the neural network. Classical activation. And when you mix this transformation and one of these activation, that's what we call multi-layer perceptron, or simple perceptron, which is available in Spark since, I think it was version 1.5. So this is available, most simple neural network. But there are some other type of layers, such as convolutional layers. I think the guy from Google talked about that yesterday, where you basically apply a convolution on the input, which can be either a 1D signal or a 2D signal, such as images. And what the layer will learn is it will learn features, spatial features, which will help it to classify or to better predict. You have another type that on which I will go into detail, which is the recurrent layer. And basically, it will learn dependencies between observations that are present, that are available as an input. So the features that you are learning are related to the dynamic. And that's what we will use both in predictive maintenance and in sentiment analysis. The objective is basically to find the best weight which minimize a certain cost function in order to predict or to classify. And the classical algorithm is the backpropagation one. I will not go into detail on the difficulties on training deep learning algorithm. There is a difficulty using this type of algorithm, especially because when you do backpropagation, the gradient tends to vanish. When you backpropagate the error, the gradient tends to vanish, and it was very difficult back in 10 years ago to train this type of network. But we found solution, actually. So recurrent neural network basic, very quickly. So there are artificial neural networks composed of at least one recurrent layer. So if I go into details, this is a typical layer, feed-forward layer, where the input xk only depend, or the output yk, sorry, only depend on the input xk. So very simple. When you talk about recurrent neural networks, it's quite different. You have still the input, xk, but it also depends on the output, yk minus 1. So there is a recurrency in that. And that's how we can capture temporal dependency. And if I unroll this through times, basically it looks like that. So you can see that yk, for example, depends also on xk minus 3. So it's basically able to cope with varying size sequence, either, as I said, as an input or as an output. 3 kinds of configuration, as I told before. First one, when you have a fixed size input, for example, an image, in image captioning, and you want to produce, for example, a text. So I have my image here, and I will produce either letters or successive words. We can call that one-to-many. At the center, many-to-many, you basically have a sequence at an input and a sequence at the output. So here, for example, I will have the speech, and here I will have the converted text. And many-to-one, that's what we'll study then. For example, in text classification, you have the sequence at an input, and you want either to classify or to predict the next word or things like that. But it's very difficult, or it were very difficult to learn. Two reasons for that. You have a lot of weights to learn in recurrent neural network. So it's more computationally expensive than traditional neural network, basically. You have the W for the X and the H for the Y, actually. So 2 times more weights to learn. So it's more computationally expensive, and you need accelerators in order to shorten the learning time. Basically, it could be either specific linear algebra library, such as BLAS, or even go to GPU. And actually, that's what we did. And you also need more data. You need more weight. You need more data to learn, of course. So there's a scalability problem. You need to be able to learn over massive data sets, and this calls for distributed learning. And some months ago, or even some weeks ago, basically the popular deep learning library, they did not offer that. They did not offer scalability over clusters. That's a bit different now, because TensorFlow, like the guy from Google said, it basically have a preliminary distributed version of TensorFlow, which can work on a Kubernetes cluster. So this has changed, but at the first, when we started this activity, that was a big problem. Second one, the simple recurrent layer, basically, they are not able to learn long-range dependency. So that's a big problem. At a given time t, it does not remember the observation between x, before x, t minus n. N could be tens or 20. And that's basically due to this architecture. Basically, the network forgets what he learns before. And the solution to that are basically new architecture. I will not go into details on that, but they basically have more memory preservation. So you have 2 types of layers, one which is called LSTM, very popular, and the other one which is called GRU. So you can see that the equation is much more complex. You have indeed 2 what we call gates. R, which is the reset gate, so basically it enables to reset the memory at a given time. And you have the Z gate, which is the update, which is enabled to control the flow of information flowing through the layer. And basically, using this type of architecture, you are able to learn dependency at different time scale. So how do we implement that in Spark? So when you talk about neural network in a distributed cluster, basically you have 2 kinds of approach. The first one is what we call data parallel. So that's what I illustrated there. Basically, at each iteration or at each mini batch, if you are using a stochastic gradient descent, there will be two things. The driver will first broadcast the model to the worker. The worker will compute the gradient of the error given their local data sets. And then, at the end of the observation, the resulting gradient will flow back to the driver where they will be average. The driver will perform an update, and then we iterate till the convergence. So that's very simple, data parallel. I will not go into detail onto the next one, which is model parallel, where basically you are able to split your model, and what you can have is basically this worker will have I would say, if we take a simple example, the 2 first layer. This one will have the 2 next, and also, so you split your neural network onto the worker. It's very efficient when you have big neural networks. a million of parameters where sometimes it cannot fit into a single worker memory. So it's very efficient for that. So we implemented all the needed blocks, transformations such as convolutional, recurrent, layers, all the optimization steps, simple gradient descent, but also more efficient stochastic gradient descent, such as RMS probe, for example, all the popular activation. But we also work on that, as I told you before. It is possible to launch the computation on CPU, but also on GPU. Maybe a few words on that. For that, you have to know that Spark, for its linear algebra operation, it relies on a popular Scala library called Breeze. It's very efficient linear algebra library, especially because it can integrate and it can be speed up by BLAST, which is an efficient speed up on CPU. But sometimes it's not sufficient. When you have big networks, you want to shorten the learning time. So we use GPU for that, and we build an extension to Breeze, which basically can compute all the operation, all the matrix operation onto GPU using GPU kernels. So that's how we can use GPU in order to speed up the learning of our network. And it's fully compatible with the existing deep learning library in Spark, which is available in Spark ML package. So a few words about the performance. On CPU, basically, you can see that it scales, and it scales very well. On a 6-node cluster, basically, you have an average of 5.46 speedup. Why do we lose some speedup? Because there is some communication overhead, of course. The information has to flow from the driver to the worker, and it has a cost. But it's nice, and it scales very well. We tested up to a dozen of nodes, and it scales very well. We have the same scalability. And it's about the same speedup as the perception in Spark ML. I didn't have time to formalize the speedup when we switched to GPU backend. But on recurrent layer, basically, we obtain up to four times speedup for some networks. So it's not that bad, and I think we can go further in order to optimize the operation. So I will leave the technical stuff about the neural network, and I will switch to the use cases. First one, predictive maintenance. To the context, so as I told you before, we basically build a lot of systems in different domains. I told you a couple of examples. And for all of these systems, what we tend to do is basically to offer more efficient maintenance operation. So what we want to do, for example, is to switch from planned maintenance every X day or X weeks to on alert maintenance. So basically to monitor all the system and detect when something goes wrong. We have a couple of experts which are very good in order to detect visually when something goes wrong, but they cannot predict, for example, given a lot of sensor curve, what will happen in the next hour. So we want to switch to go from detection to prediction. So the goal, if I formalize that, is basically to detect the early sign of a subsystem failure using data coming from multiple sensors which monitor the health of a system. So that's what we call HUMS, Health and Usage Monitoring System. So the example, on a real industrial system, so I've got 20 sensors which monitor the system. So basically the input are intensity, tension, and things like that, resistance. So I've got, for each of these sensors, I've got a value each 5 minutes. So I've got 20 value every 5 minutes. I've got the label, because the maintenance team, they provide the label, they fill the database. So I've got the label, which is useful to learn a classification model. And I will take, as a simple example, 3 hours of data and try to predict whether the system will be in failure mode in the next hour. But it's fully customizable, actually. It's just for the example. So how can I do that if I just use MLlib, popular library on big data framework? So I've got my input, and I will construct the sequence. So sequence dimension 20, because I've got 20 sensors. Very simple. the length of the sequence, I've got 12 observations per sensor per hour. So I want 3 hours, so 3 multiplied by 12. And I will construct a simple logistic regression model, simple classification model, in order to classify whether this machine or this device will experience failure or not in the next hour. Very simple, but here I don't take into account the dynamic of the system. So that could be problematic. How can I do that using a recurrent neural network? So here it's quite a low-level interface. Actually, I will construct the model using a recurrent layer here, regularization layer called dropout, a dense layer or 2 dense layer, and the last one will classify using a sigmoid function. And the impact of using this type of neural network, as we can see with logistic regression, I can detect up to 70% of the failure in the next hour with 70% accuracy, so it's not that bad actually. But if I use recurrent neural network, I can see a boost in the performance, which comes from the fact that I take into account the dynamic part of the information coming from the system. It's not only the value of a sensor, it's really the evolution that is important. And that's why when I use recurrent neural network, I can see a boost in the performance, so 15% up in the detection and more accuracy too. So that's very interesting. So if I switch to the second use case, sentiment analysis. So this is quite a simple task actually in big data domain. You have a text, you want to classify it as either positive or negative sentiment. A few words about the context. At Thales, we have built a social network analysis application, which basically can take as an input information coming from Twitter, for example, from blog, from forum, or from Facebook, for example. And the idea of this application is to analyze both the content of the text, that's what I will show, but also the relation between the actors which are publishing on a given blog or a given social media. So I actually could have shown you some other example dealing with graph analytics or something like that, but here I want to talk more specifically about recurrent neural networks. So I will focus on that, and the idea is to classify text based on their sentiment. So what I will try to show you is to explain what are the difference in this task in performance between traditional approach when you use a bag of words and then a classification algorithm such as logistic regression or machine vector or support vector machine, which are classic algorithm available in Spark already, and the recurrent neural network. So what I do basically is to take as an input all the tweets for the learning. I will not go into detail onto that, but I create the dictionary and then I transform all the text into a bag of word vector, so big vector. And then I will train, in this case, support vector machine on that using 100 iteration. So this is typical learning using what's available in Spark. And on the contrary, I will learn on the same input, I will learn a recurrent neural network, simple one, only one layer with 100 units on the same data set, and see what are the differences in performance. So the results. So if we look basically at the first 3 models, or 4 models maybe, which are naive Bayes, support vector machine, logistic regression, and a simple neural net, simple perceptron with 100 unit. Basically what you can see is the more data you have, I should have mentioned that first. Here is the size of the learning data set. 100 texts, 1,000 texts. up to 700,000 text. So what you can see here is basically the more data you have for the learning phase, the more accurate the model will be. And for the best model, which are naive bias and the perceptron, you get up to 80% accuracy on this task. So that's already quite good. If you look at the performance of the recurrent neural network, you can see two things. First, when you don't have enough text for the learning data set, you can see that it performs worse than the other model which are simpler. And the reason is that when you don't have enough information to learn, due to the fact that you have a lot of weights to learn, basically you cannot learn very well. You have to get a large data set in order to learn all the weights for those type of models. So when we switch to 100,000, basically, it starts to be a bit better. And up to 700,000, it's 4% better than traditional model. So this is more like a compromise that you have to make between the learning time. Basically, this type of model, they have, I think, they need 4 times more learning time than traditional models, and the efficiency of the model. So there's a trade-off. If you want to learn a model in a given hour, maybe you will use simple model, but if you have time to learn a more complex model, maybe you can switch to more complex one. And also the size of the data set. If you don't have, in this example, 100,000 text to learn, basically it's no use to use very complex neural network model. You should stick with very, very simple ones. So I think that's the end of the second use case. I have a few minutes left before the question, so I will maybe talk a bit about what we are doing in other use cases using this type of technologies. So I spoke mainly about classification. Basically, maintenance prediction is a classification task. Sentiment analysis is a classification task, so it's very simple example. We have other examples. For example, in airline domains, what we are trying to achieve is to better predict what we call the time arrival of an aircraft, given the meteo condition, the weather condition, given a lot of information. And for that, we also use neural network model, and especially recurrent neural network model, in order to better predict while taking into account all the available information. And that has proven also very efficient to do that. We have also other examples. So I spoke about classification, regression. There are mainly supervised algorithms. We have other examples dealing with unsupervised algorithms. What you can see is in deep learning field is that it's basically used a lot in supervised. But you can also do some very interesting stuff in unsupervised fashion. I will talk about one in cybersecurity, where we perform anomaly detection using recurrent neural networks. So basically what you have as an input is all the observation coming from a given user. So it's a sequence. You want to be able to model the sequence using recurrent neural network or other approach, but we use recurrent neural network. And basically using one type of architecture of neural network, which we call autoencoder, you are able to encode all of the sequence information into the neural network and see how the neural network can decode the information. Basically, if it can decode the information very well, that means that this observation, basically, it has seen it before. So you are able to perform anomaly detection using that. And that's what we do, basically. And it has also proven very useful in cybersecurity. So I think it's the end. So we have time for question. Thank you for your attention. And if you have question, yeah.
Thanks for the talk. I've noticed that you are using sigmoid everywhere. Have you tried fired linear units?
Yeah.
Sigmoids are horrible.
Actually, yeah, that's a good question, actually. And that's also one of the reasons why we didn't achieve very good results with very deep recurrent, with very deep neural network back in time. Because basically, sigmoid function, they tend to lower the force of the gradient when you backpropagate the error. But if you see here what the function I'm using, basically it's a rectified linear, as you mentioned. I'm only using the sigmoid at the end because I want to classify 0 if it's a failure, or 1 if it's a failure, or 0 if it's a normal state.
So it's a softmax, right?
This one?
No, next one.
It's the same. Sigmoid and softmax, basically they are the same if you want to classify in binary fashion. It's a softmax with a binary score. But that's the same.
Okay, thank you.
Yeah?
Suppose the acquisition speed of your sensor modifies. For example, they become faster or slower.
Yeah.
So my question is if you have a kind of time warping on the sensors sequences,
Mm-hmm.
is still your model valid or you have to retrain?
That's a good question. We didn't experience that in this domain. The sensor, they are basically sending information each 5 minutes. So we didn't experience this kind of problem, but basically that could be a problem, especially because what you will learn is the habits of the system, the normal behavior, and there's a frequency in that. So if the sensor information, they don't arrive at the same rate, basically you will break the frequency that you managed to learn before. So that could be a problem for this type of model. Yeah. Yeah?
When we talk about predictive maintenance, the examples that you've used, the 3 hours of sensor readings, you don't essentially get failures in that window probably. And whenever we talk predictive maintenance, we talk about rare events.
Yeah.
So how does that play in this kind of model?
Yeah.
Is recurring that RNN going to be equally effective if you have one failure in 5 years, for example?
Yeah, that's a good question. It's actually a more general question. How do you learn when your data is very skewed, when you have very few examples of positive labels? For that, we have two solutions. Basically, it can come from the data. What people do is either resample the information in order to rebalance it, or another option would be to change the cost function in order to penalize more strongly an error on a failure, for example. So that's basically we tend to do both. We have special cost function which penalize the error on a failure in order to learn the characteristic of a failure. Because of course, if you have like 1% failure in your data set, the obvious solution would be to classify everything in non-failure mode. You would get 99% accuracy, and sometimes it gets stuck on this local minima. So we penalize the loss function in order to take that into account. Yeah?
Does the recursive algorithm give successful results when the given function to analyze is not rising or falling in a monotone way?
Sorry, can you repeat?
The given function to analyze,
Yeah.
if it's not rising or falling in a monotone way, does the recursive algorithm give successful results?
From the experience that we did, the system basically, I think it definitely falls in what you are saying. It's a very complex system. You have very strong interaction between magnetic fields, between electrical fields, and I think it's fall in this situation that you are mentioning. And we basically, from what we saw, we can achieve some good performance using this type of approach. But it also can be combined with other approach. So basically, the clients behind this system, they are also working on the modelization of the system. So there is no learning in that, but they are also working on the modelization in order to take that into account. Yeah.
My
Yeah.
Given that you have rare events, positive events,
Mhm.
and lots of ways to learn, is there any kind of overfitting happening here, or does it learn the normal behavior as well?
It learned actually both, but you're right, overfitting is a big problem. Actually, one of the way we deal with that, if you look at the construction of the network, I use dropout layer on this network in order to reduce this problem of overfitting. So that's what we did.
And the overfitting is not dependent on the proportion of events, rare events?
Maybe it will have, I would say, tendency to overfit on the failure, of course, because there are not so many examples, so it will tend to overfit on that. But yeah, it's quite difficult to do that because we don't have that many observations, positive observations, so it's quite difficult to not overfit on that, yeah. Okay, thank you for your time.